dia a todos. Hoje nós vamos ter o prazer de receber o professor Sergei Kuznetsov, da Universidade de HSE de Moscou. Então, o professor Kuznetsov está na Faculdade de Computer Science. Então, ele nos deu o prazer de realizar essa visita. Aqui no Google Scholar, vocês podem ter uma ideia dos trabalhos do professor Sergei e também do impacto, né, desses trabalhos. São bem citados, bem estudados. Tá? Então, Sergei, thank you very much to be with us today. It's a great honor for us to receive you. And his talk today is about pattern structures for data analysis. And let's hear what do you like to present for us. Thank you very much.
Thank you very much, Francisca, for this kind introduction. Thank you for inviting me to this wonderful university in the wonderful city of Recife. And thank you, dear colleagues, for coming. And yeah, I would, as announced by Francisco and on the web, my main talk would be on pattern structures for data analysis. But would it be nice to introduce the university, or maybe, yeah, if you don't mind, I do it shortly. The colleagues asked me to do a short introduction.
Just click here.
Yeah, this.
Yeah.
This one. Okay, thanks. I shortly introduce my university. It's called High School of Economics. It's a very young university, like about 30 years old. It started as a really master's tool of non-orthodox Marxist economical school in 1992. It became a big university since that time. So we make jokes that HSE actually denotes a high school of everything. I personally at the faculty for computer science and heading the School for Data Analysis and Artificial Intelligence. So we have 4 campuses in Moscow, St. Petersburg, Nizhny Novgorod is a big city at the Volga River, and Perm is a city in Urals. So much undergraduate, graduate, postgraduate programs, and even a lyceum where school children start study from the 7th grade. So you see here the variety of faculties and schools, from economic science, of course, to creative industries in media, communication and design, even drama and film acting, law, humanities, Institute of Statistical Studies, Banking Institute, languages, linguistics, the engineering school, which is close to our faculty of computer science as well. So here's our department for data analysis and AI. And big, strong activity in research. And HSE takes usually 2nd to 5th places in rankings of Russian universities. So a lot of international internships, postdoctoral students are welcome, and we have many exchange programs that were a bit downscaled since the events started in 2022, but we are optimistic about the future and future cooperation with universities from BRICS, also, and of course from Brazil. We have online education programs. Yeah, and all facilities for accepting students from abroad and researchers. So I would, yeah, you will see we have so many partners from more than 60 countries. And ambitious development program till 2030. Here are the strategic projects of priorities set up by the Russian government. And here are the main areas of research, including social sciences, of course, neurocognitive mechanisms of social behavior, computer science, and other you can see at this slide. Here is our main partners, corporate partners. Maybe you know Yandex is a sort of Russian Google. It competes quite successfully in the Russian market and the community of post-Soviet republics as well. Sber is the largest bank of Russia, and MTS, one of three major mobile provider. Yeah, that's it. So much. And just shortly about our faculty. Is our dean, actually algebraist. So traditionally in Russian, computer science is very deeply rooted in deep mathematical education. So it's not surprising that Professor Arjantsov being, thank you, being an algebraist is heading the faculty, and so he's far different directions, computer science, so this sort of neutral position. So here are some facts and figures about our faculty. So we have 15 full degree programs, 16 research units, and as you see, some full degree programs are totally in English, but some actually in mixed Russian-English. Yeah, that's very important for us because these winners of all Russian Olympiads in math, physics, and computer science are best school children in Russia, so to say, best prepared in this domain. So we are happy that we have so many winners of these Olympiads. So we have Center for Student Competition. Our team is very strong at this ICPC competition in programming and data analysis and discrete math. And here are our research directions at the faculty, including, as you see, algebraic topology, topological data analysis, of course, is our the lab I'm heading is doing intelligent systems and data analysis. So we have AI Research Center supported by the government. We won the competition among 7 universities of Russia, won competition for being a governmental AI research center. So here some laboratories. This is based on cooperation with the CERN, which is now endangered due to sanctions, but we have nice analogs of CERN collider in Russia. So the research is going on. Lab for stochastic algorithms and high-dimensional inference. A lab for bioinformatics, software engineering. So some words about the bachelor program. That's how we call undergraduate studies, bachelor students. So the program in data science and business analytics, online program on data science for masters, mathematics of machine learning, really very hardcore mathematics, including Wapnick-Cherenk's theory of learnability. Our master program on data science with different application fields from natural language processing to medical information. And yeah, the faculty provides English taught programs. You see on the undergraduate and graduate level. Of course, and the doctoral school of computer science is also run in English. Yeah, the Education Center for Long Life Education. Yeah, and our faculty is organizing the Binary Super Resolution Challenge. Events like that. Annual conference called Fall in ML, where it's sort of nectar track from different conferences, mostly A and A-star level, where researchers recycle their talks at the faculty level. The talks that they gave at the highly prestigious conference like HKI, ICDM, ICML, NeurIPS, and so on. We run International Data Analysis Olympiad. It's the first one of this kind in Russia and supported by Yandex. So that's shortly about our university and our faculty. And now I would go to the main topic of this of my talk today. And first, to introduce the pattern structures, I should start with what is called formal concept analysis. It is a long story, but what is the motivation? The motivation is actually explainable artificial intelligence. And I personally is very interested in this when we are doing intensive research in this direction. And of course, young people and students are fascinated with the new results related to deep learning, neural networks. But there are many cases when these approaches fail, and including the domains where of black boxes are not accepted, like in medicine, credit scoring, engineering of complex systems, and many other. So this is just a recent encyclopedia of AI research with our contribution together with some French colleagues, Sébastien Ferré, Marianne Huchard, from Montpellier, K2, Mehdi K2 from Nancy, and me, and Amadeo Napoli, of course, from Laurea in Nancy. This is a chapter featuring this research. If you want to have a quick introduction to the domain, you can address this article in the encyclopedia, a guided tour of AI research. So let me start from a motivating example, which I took from an expert paper in the journal Business and Society. There's no agreement, no reference, but there was a paper in this famous journal, Business and Society, on the attempt to analyze banks that joined or didn't join the Wolfsburg Group, which is about joining or not joining Wolfsburg Agreement against money laundering. So here is the data set, I like it because it's not a toy, but fits in a slide. So it's not every important data are big. Sometimes and often you have to deal with small data, but then you don't need to apply approaches used for big data, which usually lose precision in favor of efficiency. And here we can provide global analysis, not just using local optimization. When we, like with decision trees, we lose many information. So the target attribute, joining or not joining the Wolfsburg agreement, is presented by the last column. Here is the list of 26 top international banks, and 11 of them joined the Wolfsburg group, and the rest didn't. So what could be a reason for joining? What can be an explanation of joining or not joining? And what are different groups made by these banks? Here you see attributes which are quite clear: the country, bank type, universal commercial investment, private, the type of ownership. This column stands for the absence or explicit or implicit code of behavior in the bank. And then 3 qualitative features staying for measures of corporate coordination, financial liberalization, regular intensity, as measured by experts in the domain. And the last but one column is quite clear, is being or not being on the blacklist of International Monetary Fund. Yes or no? So what makes a bank join the Wolfsburg Agreement? Having the other features of the bank given by these attributes. Let's see that we have dependencies like this. If a bank type is commercial, then the bank joined the agreement. That's one type of dependency we call implication, and we'll consider it formally further on. Yeah, that's important observation for in this world. But implications can, another observation of this kind: if bank type is private, then the bank didn't join this Wolfsburg agreement. That not all dependencies are deterministic in the sense that A implies B always. Here's an example of what is called association rule. When bank is of universal type, it is public and has explicit code of behavior, then it usually joins the agreement, actually with confidence, as they call it in data mining, or actually conditional probability 5 over 6. What else can we derive from this table using our tools, which I just announced here, and I will present you with formal definitions of that. That we can think of possible queries. What are banks with high regulatory intensity, with reg int more than 200? These are Barclays, Citigroup, Coutts-Co, and so on. But what are their common properties? Turns out that besides high regulatory intensity, they are also on the blacklist, and the financial liberalization is the highest possible. And of course, the initial property given by the query is that these banks have high regulatory intensity. So we have a sort of cluster of similar banks defined by similar properties given by common attribute values. And more properly, this should be called not a cluster but a bicluster, because we don't have an explicit distance or similarity measure which we use to cluster objects, but we use rather sets of attributes, set of attribute values to say that these objects, these banks, make a cluster because they share common descriptions. That's the idea lying behind this notion of bicluster or co-cluster. So having this motivating example, let's proceed and make definitions that would allow us to make this to show the formal foundation of these tools and suggest some algorithmic tools for computing them. So we go to the domain of formal concept analysis, which starts from in the simplest form from a binary data matrix, and further on I will show how to extend it to more complex data like numerical and graphs, strings, and so on. Here, just before giving formal definition, I would say that this pair 3,4 BC makes so-called formal concept, with objects 3,4 being the extensional of the concept, and BC expressing the meaning or intent or intentional. This formal concept is seen as a subtable filled with crosses and maximal by inclusion with respect to this property. If we want to add a column or a row, we would get an empty entry. Actually, this idea of a concept is very old. It dates back at least to the Logique de Port-Royal of the 17th century, where Antoine Arnaud and Pierre Nicole defined the concept in a qualitative way as a pair, what they called in that old French, extendu et compréhendu. So extension and comprehension in modern terms. And they even observed that the larger the extension, the smaller will be the comprehension, if described in formal terms, but they didn't do it at that time. It was the time when mathematics were mathematicians were doing physical models, not informational models. So it was not surprising. Then this another French genius, Évariste Galois, actually defined this, proposing his theory is based on two mappings from the field of polynomials to the group of the automorphisms, and back from the automorphism groups to the fields of polynomial. And these two mappings were abstracted by famous mathematicians like Gareth Birkhoff, Ore, Øystein Ore, and then extended by modern French researchers Marcel Barbu and Bernard Monjardet, to define an abstract Galois connection between two ordered sets. And Rudolf Wille, a German researcher, published this seminal paper long time ago, and it was based on the previous work of these famous mathematicians. the general idea is as follows. I would rather use this standard, they call Darmstadt notation. If we have a data table, a binary data table with rows, which can be represented by, where rows stay for objects and columns stay for attributes, denoted by sets J and M respectively, from German Gegenstand Merkmal, objects attributes, so that prime operators are defined as follow. For a subset of objects A prime is the set of all common attributes of objects from A. And for a subset of attributes B prime is the set of all objects sharing all attributes from B. These two mappings, with a slight abuse of notation, denoted by the same symbol prime. Actually, to be pedantic, you need to denote them differently, but we usually use one symbol for that. We make a global connection between power sets of objects and power sets of attributes, so that a pair AB, a subset of objects, subset of attributes, is called a formal concept. If A prime equals B and B prime equals A. B is the set of all attributes of objects from A, and A is the set of all objects sharing all attributes from B. Like in this example, here 3,4 BC makes a formal concept, where 3,4 is its extent and BC is its intent. Yeah, with numerous applications in gene expression analysis, sociology, NLP software engineering, thousands of papers. I wouldn't concentrate on this, but I would rather show you a simple example here, that these concepts are ordered with respect to the extent. So this, for example, this extent is a superset of this 3,4, and this is a subset of 3,4. So they are ordered, and this is a diagram of this order, called also Hasse diagram of an ordered set. And the very important property of this ordered set is that it makes a lattice, because for any two concepts there's a unique supremum, being the most specific concept that is more general than the two, and unique infimum, which is the most general concept with this, which is more special than the two. We know supremums and infimums in orders in the set theoretical version, but here and generally lattices can be not distributive like they are for Boolean lattices. In the case of Boolean lattices, here's an example of a non-distributive lattice. Actually, if you probably know the famous Birkhoff theorem, saying that if a diagram contains pentagon, then it's not a distributive lattice, but it doesn't matter for our studies here. The important thing that with this diagram we can represent a taxonomy of the subject domain. So, for example, this concept can be interpreted as figures with the rectangle. These are equilateral figures, and 1, 2 are triangles, and 3, 4 BC stay for rectangles. Yeah. So we obtained taxonomy of possible classes of subject domain. As you see, the classes may intersect. Like here, 1, 4 and 2, 3, 4, they have common element, and it makes actually the infimum of these two concepts. 2, 3, 4 and 1, 2 as also intersect as clusters of objects, and the intersection is given by this concept. So the primes have some wonderful properties which are easily to show. They are anti-monotonic, their composition is monotonic, they are extensive. Double prime is idempotent, it's De Morgan law, and some other properties that would allow to call double prime operation, the composition of primes, a closure operator. So we refer to it as a closure. Here's an example of equivalence classes of descriptions which are given by sets of binary attributes like AB, ABC, ABD, and they form equivalence classes with respect to sets of objects they describe. For example, B and BC describe the same set of objects. BD, CD, and BCD describe the same set of objects, namely the set consisting of one element 4. BC, B describe 3, 4 set. And this all descriptions describe the empty set of objects, since no object has both A and B, ABC, and so on. These equivalence classes are, have interesting structure. They have unique maximal element. Here, the diagram is in the way that maximal are below. These maximal elements are denoted by red. Maximal with respect to set theoretic containment. Yeah. And they correspond to closures, closed sets of attributes. And the green one correspond to minimal elements of equivalence classes, and they are called minimal generators. Closed set of attributes are also, as we already said, are called intents or intentions. So you see that these prime and double prime operations compress data into these classes. They are not 2 to the 4 sets of objects, but just 9. So many as are equivalence classes. Not 2 to the 4 sets of attributes, but only 9. So they these operations compress data, and we can consider closed sets of attributes or intents as representative of each class, because it's the unique representative. The minimal generators can be many, actually exponentially many in general case. As you see here, we have several minimal generators in these classes. And another important aspect of this model is related to so-called implications. We have for 2 subsets of attributes A and B, the implication A implies B if A prime is a subset of B prime. So all objects having A also have attributes from B. Implications satisfy Armstrong rules, which are well known in database theory. They are actually cryptomorphic to functional dependencies. We can translate functional dependencies in implications and implications into dependencies. So having these rules, a natural idea is to propose the smallest amount of implications such that all other can be derived using the rules. So we don't need to store all implications, we need just some base of implications from which we can derive all the rest. As I mentioned already, the implications are closely related to functional dependencies in databases, and they also, from the logical point of view, actually cryptomorphic to Horn theories. This decidable fragment of easily decidable, linear decidable fragments of first order logic, and here is in propositional form. Actually, implications can be seen in a diagram. Like C, here you see when we have B, we always have C. So B implies C. And this is seen that the concept corresponding to B, 3, 4, BC, is below the concept corresponding to C, 2, 3, 4, C. Now, generally, the relation is visualized as follows, as written in this upper lines of the slide. Actually, implications are make partial case of what is known as association rule in data mining. These rules were, I would say, rediscovered in 1990s and still make an important tool in data mining. Here, we don't have always B when we have A, but we have it with some conditional probability called confidence in data mining. That means this denominator stands for the number of objects having both A and B, and here for the denominator stands for the number of objects having A. And surprisingly, the most concise representation of all association rules is given by the diagram of the lattice, which is hence becomes not just the tool for visualizing hierarchies, but for being concise, most concise representation of all probabilistic rules in the data. So here, with red numbers, I showed the confidence of the rules attached to each edge. So from D, you have D implies BCD with confidence 1/2, because we have two objects having D and one of them has also BCD. So C implies BC with the confidence 2/3, because we have three objects having C and two of them have B. Yeah? Actually, any rule of the form A implies B, where A and B are arbitrary, can be expressed as a combination of rules attached to every edge of this diagram. And it's interesting that this empty implies BCD, meaning what is the frequency of BCD? Is 1/2 times 1/2, 1/3, 1/4. That's the frequency of BCD. Or you can go this way, 3/4 times 2/3 times 1/2, again 1/4. So the product doesn't depend on the way you go, just depend on the initial and final point in the diagram, which corresponds to an association rule. And as for support, there's an important property that supports goes down while we moving top down. So if we want to constrain to take good rules with high support and high confidence, we take only rules attached to associated with the edges of the diagram, and only upper part of this diagram. Say if we constrain our support by 1/2, we don't need to go below this anti-chain. Don't need to go down. just computing the upper part and ignoring the rest. So another example how we can apply, now it's a example how we apply these constructions in a learning setting. Suppose we have a small robot that has only 4 measuring devices for measuring color, firmness, smoothness, form of an object, and it is given 4 positive examples of fruits and 3 negative examples. So it has to produce some classifier that would distinguish fruits from non-fruits. So then we first binarize data. First we do it, and later on I'll show how we can avoid this. So the color, white, yellow, green, blue, firm, non-firm, smooth, non-smooth, round, non-round. And since we cannot apply statistics, what's the use of applying statistics here? Too few data. So let's reason as follows. Fruits should have some similarity, which wouldn't make them similar to non-fruits. For example, apple and grapefruit are both yellow, non-firm, and round. Yeah, that sounds a good hypothesis. But if we take similarity of all 4 fruits, it's just non-firm. It's not good because the tennis ball is also non-firm. As for non-fruits, there's a good hypothesis for being a non-fruit if it is white. Like egg and tennis ball, there's no counterexample in the positive examples. So if we look for hypotheses as similarities of objects, that mathematically means that we look for hypotheses intersection of sets of attributes describing every object. So row-wise intersection of the binaries for binary representation of sets. And intersections make a closed set of attributes or intents. So that's why we are back in this world of closed descriptions, because every intent is an intersection of a row here. So we see here the lattice, the diagram of the lattice of positive context. With this good hypothesis, there's a generalization of descriptions of positive examples which do not match any negative example. This one is not good because non-firm, non-smooth are also attributes of the tennis ball. So this is sort of falsified generalization, which we wouldn't use as a classifier, as well as just non-firm, the generalization of all positive examples. So negative example constrain our attempts to generalize as much as possible. They make us more modest in our generalizations. So finally, we can do the same thing for negative examples. So we have white and firm, smooth, and non-round would be a good hypothesis for being a non-fruit. And then if we get some new object like mango, which is yellow, non-firm, smooth, and oval, then we see that it's likely to be classified as a fruit because there are positive hypotheses in favor of it and no negative hypothesis in favor of it. And we get a piece of white soap. It is classified negatively because it's white, and none of positive hypothesis is subset of the set, so classified negatively. But I wouldn't make this a totally success story. Like we can have, of course, fallacies like here with the champignon. Can be both arguments for it's being a fruit and for it's being not a fruit. And with a watermelon, you have no arguments at all. So this is just a toy example, but you see that there can be that in this case we need to, in practice, we need to reconstruct our set of attributes and add new objects, and maybe think, maybe the notion of a fruit is not very nicely defined at all. Yeah, what is a fruit? Everything is fructus in Latin. Yeah, that's just everything. Like tomato is also fructus, but this human understanding of fruit is ill-defined, actually. So, so back to the data set of Wolfsburg agreement. Quite practical example. We see that we can see now that if we binarize this data, I didn't do it because there will be a blow up in the attributes, but you can realize that every many-valued attribute can be represented by several binary attributes, each of them staying for the attribute value of the initial table. So then we'll have then this group of banks described by their common properties as a formal concept. The list of the set of banks makes the extent of this concept, and the set of binary attributes would make the intent of this concept, the meaning, so to say, or description. So we now have the formal model to describe what we obtained here, and actually we can have a hierarchy of such concepts, making taxonomy of the domain, and then this is really an attribute implication, as we defined it formally. So all banks being commercial have joined the agreement. All banks that are private didn't join. So we have an implication, and we have this association rule, which actually corresponds to an edge in the diagram of the lattice of all concepts related to this data. So we that was the basic model. We have algorithm for that, but I don't have time to go into detail. I would just there's no time for that. Just mention the good properties of the algorithms. Although in the unconstrained form, this algorithm can be exponential because the number of all possible concepts is exponential if we don't constrain it in any way. But the time complexity looks as follows. G is the number of objects, rows, M is the number of columns, and C is the output, the number of concepts we output. So if the number of concepts is small, then the whole worst case estimate is also polynomial. And the amortized complexity, so complexity per output is this, and we just divide it by the number of concepts, and delay the time between two consecutive outputs of concepts is also polynomial. So these are good news. Since we have also tools for constraining this size. How we do it? We use the anti-monotonicity of support. For example, we compute only to some threshold a top supported concepts, for example. If we take it a fixed number, k, then we compute only them, and then we have polynomial time algorithm. Because as I showed here, as I showed you here, the delay is polynomial. So instead of size of c, we have k, and k can be constrained. So so far for the basic model, and now I would go to model with complex. So far we consider data which are categorical, binary, and we know that we can reduce numerical data to these forms of data, but we would like to work with structures directly. And the applications we worked with are related to chemistry, chemoinformatics, the so-called structure-activity relationship, when you need to find pharmacophores, as they call it, structural causes of biological activity. Like here is a toy example, but it's close to reality. So, for example, we have some biological activity, say toxicity, and we have 4 toxic substances and 3 similar to them, but not toxic. So what is the structural cause of toxicity? This should lie in the similarity of toxic structures, which shouldn't be common to non-toxic structures. It's not easy to see it directly, and if we represent these structures by attributes directly, then we lose a lot of information, and we probably wouldn't get any explanation of toxicity. So in acting in the same way as we did with binary attributes, we need some sort of intersection operation between, because as we saw in this toy example with fruits, we looked for similarities of object descriptions as intersection of sets representing them. So what will be an intersection in the case of graphs is not clear, because if we say for 2 graphs, let's take as an intersection its common maximal subgraph. Yeah, because that would be the first idea, because what is intersection of 2 sets? It's just the maximal common subset. Yeah, is the intersection of 2 sets. So, but in case of graphs, this definition is not unique. As you see for these 2 graphs, for example, where these labels CH3 or HC stay for labels of vertices, and this bonds color, double bond and single bond stay for labels of edges in the graph. So they can be multiple common maximal subgraphs. This one is maximal common subgraph of these 2, and this one as well. So I mean, maximal not in the size of in the number of vertices, but with respect to containment relation, actually subgraph isomorphism relation. So we cannot extend this in any way to make it both a subgraph of this and this. So the solution, a possible solution, is to take them all. Starting from this initial order on structures, on graphs, we use the not the we use this order. This is a generalization, but we wouldn't use it here. Just the idea how to generalize. This is just a subgraph isomorphism relation. This graph is isomorphic to a subgraph of this. In the sense that you can define a mapping from vertices of this to vertices of this that would respect edges and labels of vertices and edges. So this vertex with this label goes to this vertex with the same label. This goes to the vertex with to this vertex with the same label, and so on. And this edge with labeled as double bond goes to this edge labeled as double bond. Yeah. So this is the basic relation, subgraph isomorphism. And we build upon it this operation of intersection. Since the result is a set of graphs, we need to define it also on the set of graphs. So we put here braces denoting this singletons, sets consisting of single graphs. And the result of this operation is given here on the right side. And then we can define operations on graph sets as an extension of this. So to intersect this with this, we intersect pairwise from here to here, from this, and then we take the union and take maximal elements. Maximal with respect to this relation subgraph isomorphism. And we obtain this one. So what we get for this example, we get the following picture. So here we have the original structures, 1, 2, 3, 4, original positive examples. And then go the intersections. The intersection 1 and 2 is this. Intersection 2, 3 is this one, set consisting of two graphs. 3 and 4 is this, and so on. Actually, we define the same, as you see, we obtained a diagram of an ordered set of descriptions, and to each description is assigned to a set of objects. So here we have, for example, 2 and 3, meaning that intersection of description of 2 and 3 gives you this one. And as if we start from this, then we get objects 2 and 3, the complete set of all objects that match these descriptions. So we don't have, for example, sets of objects 1, 4, because if we compute the intersection of 1 and 4, we get this set of graphs, which would match also graph 2 and 3. And so we finally come to the similar situation as with binary attributes. We come to what we call pattern concepts. Extents are given by sets of objects, classical sets, and intents are now sets of graphs. So more general description than binary attributes. So, and this is captured by formally by the following formalism, which we defined by Bernhard Ganter, my Humboldt professor in Dresden, Germany. GD delta makes a pattern structure if G is a set of objects, and D underlined is meet semilattice. So it is consists of set of descriptions D and operator of intersection, which can be understood as taking the common part. And delta is a mapping from objects to descriptions. So this is sort of generalization of formal context, where instead of set of attributes, we have descriptions. And instead of the table, we have this mapping description. Each object gets a description. You may say that having a semilattice like here is another word for infimum. Maybe it's too restrictive, but not as you can see. Actually, there's nothing restrictive in these definitions. This definition here doesn't mention graphs at all. It's based on a partial order on descriptions, and this partial order can be of absolutely different nature. Here you see as well, there is no mention of graphs here. Just what matters is this relation, which for graphs is subgraph isomorphism, but can be any part of relation. Here we took it like part of a graph, formally isomorphic to a subgraph, but we can take it as a basic relation, any relation on descriptions and their parts. So here we see that we have the same type of positive hypothesis like we had with fruits. This makes a good hypothesis, this as well, but generalization of second, third, and fourth example is not a good hypothesis because it's falsified by negative example. It matches description of a negative example, so it's not good as a hypothesis about toxicity. This as well. Everything which is above falsified is also falsified because this is smaller description than this one. So it also matches the one which matches this one. Yeah, in what sense smaller? You see, this is set of two graphs, and this is set of one graph. But it is smaller in the sense that every graph from here is isomorphic to a subgraph of this. So in this sense, this is a smaller description than this one. And this, for example, is a smaller description than this, although here we have two graphs and here is only one. So we also, with this diagram, we have association rules. For example, this thing implies this, or let's say this one, this one implies this one. With confidence 2/3, because we have here in support 2 objects and here we have 3 objects. So the confidence of this rule from this to this is 2/3, which means if we have this in a description of an object in our database, then probability 2/3 will have also this description in the object. And we have not only hierarchical taxonomy of classes in this domain, but we also have this hypothesis, association rules, and implications in the same way as we had with binary descriptions. Yeah, here are generalizations of primes. A diamond is intersection of all descriptions from the set A, and for a subset of objects A, and for a description C diamond is the set of all objects matching this description C. And then a pattern concept is pair AC, where C is A diamond and A is C diamond. Like we had it here. So we made a lot, actually, many things in data mining were redefined because it turned out that closed sets are a very useful tool for compressing data and closed descriptions as well. So it was, but I don't have time for that. I would address the following issue that, okay, maybe looks nice in a picture, but we know that computing subgraph checking subgraph isomorphism is an NP-complete problem, and computing maximal common subgraphs even an NP-hard problem. So we need to do something, and we proposed a tool called approximation tool called projection. It's a monotone contractive and idempotent operation. Like, for example, we can project initial graphs into sets of connected 3-vertex subgraphs. And then we have nice properties, and which, yeah, I'll show it here. Here we have 4 projections. We project initial data into sets of subgraphs with only with no more than 4 vertices. Looks maybe more complex, but if you have big data and big graphs, then projecting to 4 vertex subgraphs makes information, you reduce information. But as you see, we still get we get the same structure even if we projected, so nothing changed, but we gained in computation efficiency. We can project even stronger to 3 vertex subgraphs, decreasing the complexity, simplifying the structure, but we still have something reasonable like this hypothesis, for example. Yeah, as generalization of first, second, and third examples, it is not falsified. But if we project too strongly to 2 vertex subgraphs, then we get a mess, because the initial substance structures are quite similar. If you simplify them, then you wouldn't get anything reasonable. So this picture shows you that we shows you actually the dimension, an example of dimension curves. We need to choose a balance between complexity of representation and efficiency of algorithms. So probably we could have stopped here, but not simplify too much. So we made, I wouldn't show you many tables about best results, that we just many experiments in chemistry, and we also use these approaches for problems in natural language processing. Here we use the construction that we call parse thicket. It is based, consider this picture, this figure. Here's a parse thicket of a text with 4 sentences, consisting of 4 sentences. Every sentence is parsed in a standard way. It's a syntactic tree of or parse tree of a sentence, individual sentence, given in gray, and then we add to this 4 unrelated trees semantic links, semantic edges, staying for example, anaphora, where a noun replaced by a pronoun in another sentence, same entity relation, hyponym, hyperonym relation, and maybe some links from modern linguistic theories like rhetoric structure theory, speech act theory, communicative actions, and so on. So here, it's not very visible, but same entity, communicative action from the speech acts, then anaphora, same entity, anaphora, mostly like that. So what would it give us? So, for example, we have two paragraphs. So suppose the problem is to cluster texts. And we have two small texts like this. And if we represent them in a standard way by bags of words, then we get something not very informative. Maybe some idea about what about, but not exactly the meaning of these two sentences, of the two paragraphs, which actually are quite close to each other. And then with these sparse thickets and our approach based on graph similarity, we can detect that these texts have similarities given by green, circumscribed by these green curves. These make isomorphic subgraphs of these two graphs. Each of these graphs stay for a paragraph. So we can cluster this text based on their structural properties, these structural properties being defined by syntactic and semantic relations. Here's another example where we have four small customer reviews on some MacBooks, and we cluster them. Here's the cluster of all reviews with very basic common features, like is noun phrase, MacBook, Air, CD, what is it? And here are classes of more similar reviews. R1 and R4 are similar in this, with this description representing their similarity, and R1 and R3 are similar with this description expressing their similarity. And here are the initial reviews. So here we also have association rules, taxonomy, and implications, and we can build hypotheses in them before. Another example of a pattern structure, which I would like to dwell on tomorrow in more detail, is related to interval data. Actually, interval pattern structures, because we can start from just numerical data and define a similarity operation, this intersection or meet or infimum operation, as taking the convex hull of intervals. For example, you see for the rows, the first two rows of this table, the similarity of them would be expressed in the following way. Interval from 5 to 6, interval from 7 to 8, and interval from 4 to 6. Yeah? And so this is a box stays like a diamond. So taking the diamond of these two sets gives them the common description, which covers both G1 and G2, and being the smallest description which covers them. And if we go back to objects, so we take the diamond or box of this description, we arrive to the fact that the object 5, given by the fifth row matches this description, because 5 is between 5 and 6, 8 is between 7 and 8, and 5 is between 4 and 6. So we get back three objects instead of original 2. So this pair, object 1 to 5, with this description makes a pattern, interval pattern concept. And the meaning that I gave in the formal definitions before. So with this we analyzed gene expression data, which are usually of this form, where objects stay for genes and columns stay for proteins, and the entries stay for expressions of genes in proteins. So the bioinformatician would like to have groups of genes described by similar activities in proteins. So this would make a sort of bicluster with they clustered on two sides, objects and attributes, which in Euclidean space can be seen as a in this case, three-dimensional parallelepiped with edges and faces aligned with axis and planes made by the axis. Yeah. Sorry, what's the time? How much is left? Okay, and yeah, maybe that's an approach that we study now, that that's avoiding construction of big amount of classifiers. We are now researching so-called lazy strategy, where we don't produce all classifications from the training set, but we we classify on demand, a query-based or lazy classification. We intersect a query, a new object with a known target property, with positive and negative examples, and then we positive and negative intersections to conclude whether a new object is rather classified positively or negatively. This is can be seen as a version of nearest KNN approach, but based not on similarity metrics or distance, but on common properties. Yeah, and so to conclude, I would say that pattern structures are a convenient tool for construction and visualization of taxonomies of subject domains, where data are complex, not just binary data, but numerical, structural, like graphs, strings. And they provide tools for finding implicational dependencies, such as implications, association rules, and hypotheses, such as hierarchy of approximations in terms of projections, and allow for lazy evaluated classification with obvious possible ways of parallelizing and randomization. And thank you for your attention.
Thank you very much for this nice presentation. I would like to, we have some time to some comments or questions if you would like. So, someone has comments or questions? Yes, please. Excuse me. Use that because this is there is a transmission in YouTube channel.
Okay, the similarity you mean is between the vectors, the format, or it's just like the median distance, for example?
You mean for numbers?
Yes, the format of the graph.
Yes. This is. You mean
you transform your binaries in a graph, for example, this graph?
No, we don't. We compute with graphs, but I made it here an important point that actually we can actually we can represent it in equivalent form by a lot of binary attributes. There will be big tables. In theory, we would need then all subgraphs of every graph represented as a binary attribute. Then projecting would mean reducing some attributes, like shown here. Yeah, but
okay.
We don't need to go to binarization. We can perform with graphs.
Okay, got it. Thank you.
Other comments or questions?
Okay. I have a question regarding what this approach. How would it work with regards to uncertainty? Like with uncertainty, like stochastic processes, random things. Like for instance, in the graph of concepts you put right at the beginning, where you show the confidence between the concepts, more or less distance measure. It was based, you interpreted them as probabilities, but that would be using the classic definition of probability, right? In terms of the permutation of the possible cases. But if you're dealing with actual data and uncertainty and errors of measurement and so forth, then you would have to use something like relative frequency as an estimate of probability. And then a graph could be very different from the one that you showed, for instance.
Yeah, that maybe I didn't get it completely, but speaking of probability, of course, I mean frequency in the data we have. You see that sample-based probability, if you want. Yeah, that's. I mean probability in terms of frequency in the data set, like here, like with where is this example with the figures? Yeah, here.
Here,
for example. Yeah, this probability as a frequency in this. Yeah, I can interpret this because this is correct, but in some sense only.
Yeah, but I see. But in that particular case, in the geometric shapes, for instance, I know it's just a toy representation, but in that case, every particular observation is unique.
Yeah.
And you don't have repeated observations of the same things, where repeated observations can lead to different results, as happens in stochastic phenomena. Because when you have it like that, then the relative frequencies, they converge to the classical definition. But when you have the possibility of repeated observations leading to different results and different categorizations of the attributes, then you would have a very different result, right?
Yeah.
Is the method robust to that? I mean, because when you get into that, then you have to think of confidence intervals and margins of errors and
Mm.
probabilities and so forth.
Mm.
Or maybe the method is just more suited for smaller samples.
Yeah, that's as well, but we have, I didn't touch this, we have actually we use a measure of robustness called stability, which is based on the idea like leave one out or jackknife, where you check whether your intents are retained when you delete objects. In modern terms, this is called ablation study. So if we delete objects, then would the resulting intent, the set of attributes, stay or disappear? For the stability would be high if the ratio of the cases where the intent remains is high and is low when it's low. And this gives a good measure because it's anti-monotonic. We can start with most stable patterns, most stable closed sets, and then come to a certain threshold of stability and then ignore the rest, which would, to our understanding, not reliable, maybe artifacts of representation.
I think that is quite different approach. This approach is based in logic, and maybe what you mean is approach based in probabilities and inference and so on. This is quite different approach.
So
I have an observation.
Sorry, I would say that the intervals give also some. You can interpret this as uncertainty in data because you can start with intervals in your data. Yeah, this can be used as a sort of fuzziness, the interval.
No, my observation is your approach can produce a lot of concepts.
Yeah.
And then how are the tools to find the interesting concepts? Is confidence, like something like that? You need to search a lot, or you can do this very quickly.
The one I mentioned here is the interest. So there are actually many interesting measures. Thank you. I didn't include it in my talk, but maybe I will do it tomorrow. The one is certainly support, which I mentioned. So on top of this diagram, we have most supported patterns. Yeah, and as we go top down, we get less support. So we have set a threshold for support. We should stop somewhere, and we have measures like stability. That says that actually describes how a representation, how a pattern is stable or robust with respect to throwing away the observations, the objects. And there are other interestingness measures. We made a survey on that. One of them is based on the so-called basic level concepts, which is the idea of Emily Roche, is a famous psychologist. And this interestingness measure was studied by Czech researchers in the group of Radim Belohlavik.
Okay. Any questions or comments?
Thank you for this fascinating talk. I have some notes here. First, when you approach the chemical problem, there are some situations in chemistry where actually the symmetries of the molecule matters. So this would be like an isomery, things like this. So actually this would be an additional information on the molecule. And in this case, it will suffer a lot from projections and all, and you need to be attached to a different scheme in the semi-lattice, etc. So have you approached this somehow?
Thank you. That's a very nice question. Yeah, indeed. Here, in this setting, we cannot approach isomery, but it should be introduced as special descriptors. You see, coming from binary attributes to graphs makes you computationally harder, but going to 3D is becoming terribly hard. So we'd amend these descriptions with special descriptions related to isomery.
Like group presentations?
Yeah.
And then when you consider this, that's exactly what I was thinking. If you do a group presentation, what is your rule to pass between them?
We make a composite description. Part of it is a graph, and parts can be given as binary attributes, saying this or this, right or left, for example. So we get a tuple where one element stands for a graph and other support this three-dimensional. Because to make it full-scale three-dimensional is very hard. You need to take into account all angles, all distances. And actually we come to the problem of, how do you call it? Not convolution. Actual three-dimensional objects, the conformations, because every substance can have thousands of conformations. If you go to 3D, which one of them you should take? They can.
You have to take also consideration if it is chemically possible, requiable, because the total combination can be for the rules of chemistry.
Sorry.
Naturally possible.
Sorry.
My question is like some of this permutation maybe is not chemically possible, so you have to verify that, I suppose.
No. These are treated as fragments, formal fragments. They are possible because they happen. They occur in real substances.
Okay, so
they are not possible as how to say. They are not substances. They are fragments.
Yeah, but don't you combine those fragments, and then in this combination, is it possible that you can generate things that's not chemically bound impossible?
Yeah, this and this. Yeah. For this, we have this one as a realization. You see, there is. This is a set. It's not a disjoint graph. It's a set. This, comma, this.
Yeah, I know,
that means that these patterns, these subgraphs occur in some. So these are just parts.
No, I understood that, but aren't you combine those sets? And my question is, if you make a combination, is it possible that you come up with combinations that are not chemically possible?
I understood that, in fact, the graphs are attributes. I understood, or I missed something. The graphs function as attributes. No, not really. Okay.
Almost like, but they follow different.
I think there is a misunderstanding. The vertices of the lattice are real substances, and you're extracting from them fragments to do the analysis. You are not reconstructing things from the fragments. You are just taking from real molecules fragments to do the pattern recognition. So you're not rebuilding all the possible theoretical combinations. No, you are starting from real data that are the molecules, and starting. Otherwise, you wouldn't need a lattice. You would just make all the possible things in a huge lattice. This is the real lattice from real data. That's why it has a semi-lattice, of course. That's why it has a particular configuration.
Then how do you compare that with using, let's say, classical method, like, I don't know, if you use random forest or some other classical machine learning method, how do you compare that? Because you can do that
Which
with
one
other.
you mentioned?
I mean, if you compare with normal classical machine learning methods like random forest or I mean, the first example for me looked very similar to Bayesian classifier that you use. I mean, basic probability. I mean, so how can you comment how you can compare those methods? Because here you follow a very kind of a rigid mathematical graphical model.
Do you see? Of course we can. You mean this one? Yeah. Yeah.
Maybe perhaps one
That's
could.
a good point, because if we compute a decision tree, then it will be biased. It will show just one of possible solutions here. For example, if we use a decision tree, it will be white or non-white. Finished. Yeah, but here we produce a global view. In a sense, random forest reduces this biasness of decision trees in a stochastic way. We suggest a global optimization, a global view on that. Here we have everything in this picture. Yeah, so for small, we can, if we don't have really big data, why should we use methods like decision trees? They are biased, and random forest is just in a strange way trying to compensate for their biasness in a stochastic way. But if you produce 100 trees with 10 vertices, is it a good explanation? I don't think so.
Perhaps we could simplify that just by saying that the method never produces a concept that extrapolates the data. So therefore, it will never produce an impossible result, because it's all concepts are subject. But that is also a limitation, because the concepts never extrapolate the data. So it's hard to use that to generalize, for instance. It's both a strength and a weakness.
So coming back to this, these are just fragments of description. We don't claim that they make substances per se. They parts, like in chemistry, they have the notion of radical. It's some part with non-saturated valences, some clearly, implicitly, explicitly described part with something with sort of question mark. It's radical. Something can be put there. In the same way, it's here that These are fragments. They describe classes of possible chemicals that match this description. Among them, there can be formally non-valid chemicals, but we should match them to valid molecular formulas to obtain classification. Did I answer your question?
I think your motto is semilattices provide much richer explainability than decision trees, or the structure simpler, right? But I have two questions and we have less time. First, okay, we are in a mid-semilattice. Are there examples of interesting join attached to these mid-semilattices? Are they unique? Do they have any meaning, or they are boring?
Good question.
Okay, but then let me make the order, because we may like the order and we have little time. Galois connections and semilattices and lattices are examples of categories in category theory. Is this formal concept analysis, I'm new to this, generalized or imported tools from category theory? Thank you.
Excuse me, Sergei, before you answer. So we will need to stop very quickly, and we can continue to discuss, because there will be another meeting here now. And then thank you very much for your attention. And thank you also for Sergei to this very nice presentation. Then you can
I will answer you.
You have just 5 minutes to conclude.
Yeah, 5 minutes.
Okay.
So, a very nice question first. That you see, finite mid-semilattices are almost lattices. You see, I put this dummy here is a dummy. So finite semilattices are easily completed to a lattice. You put just one top or bottom, and then you get formally the join, the supremo. Yeah. So for these two, it's this one. Yeah, it's just like that. But we actually don't need it much. It's enough, because this neat infimum or similarity is semantically important. It gives the common part. It gives a common part. As for category theory, we are close to these tools are close to it. I know that in category theory they consider equivalent connections and the dual adjunctions, and we actually with Francisca yesterday we considered this axialities as adjunctions on power sets, which would to my mind, and I have some preliminary work on that, would help to catch dense clusters through density. With this approach, for example, you cannot distinguish easily this, for example, two half moons or two encircled patterns. But with axialities, you can do it easily. So it has the influence, but we don't use it in practice, so to say. And by the way, the colleagues showed that pattern structures make a different category than the formal context.
Okay, Sergei, thank you very much. So we'll start to finish. There is some technical things to do before finish. And then thank you very much for all. Obrigado por todos que compareceram. And thank you very much, Sergei, for your nice presentation. Continue after to talk.